Don't stop me now. Don't stop me, cause I'm having a velocity time, having a displacement time. Okay, you know that something. Alright, so we are moving on to kinematics, which, as you guessed from the lyrics, is about velocity time graphs and displacement time graphs. Okay, so first of all, let's discuss gradients and areas. And on this grid, I've got a lot of different colored lines, and I want to know what is the gradient of those. What are the gradients of each of those lines? So what is the gradient of each of those lines, I mean. So if I take, say, the green line here, what I want to do is pick 2 points on the line. I want to pick 2 points that are quite far apart, but ideally ones that go through these intersection of whole numbers. So I can choose the origin as one of my points, and I can choose that point there. And so the gradient is how much do I have to go up and how much do I have to go across to get to that point. And so I can see I have to go up 4 and across 2. So the gradient of that line is 4 over 2, which is 2. So this line has got a gradient of 2. If I wanted the blue line instead, then I would pick, say, this point and this point. And I'd say I have to go up 5 and then across 5. So the gradient is 5 over 5, which is 1. So this has got a gradient of 1. Okay, gradient of 1 means at 45 degrees, but that's only if we've scaled the x-axis and the y-axis with a 1-to-1 scale, so that they're going up by the same amount with the same size gaps. So gradient of 1 would be 45 degrees. These gradients are less than 1. So they're less than 45 degrees, they're less than 1. So this gradient is probably a half, and this gradient maybe a quarter. And then these gradients here are more than 1. We already said that's gradient of 2, and that gradient might be 4. And then obviously if you get to a really steep line like this one here, a vertical line, then its gradient is, well, we can call it an infinite gradient, or we can just say that gradient is undefined for that line. These grey lines have got negative gradients. So this one here has got a gradient of -1. So this one here has got a gradient of -1. And this one will be -2 because it's steeper but downhill. And this one will be -1/2 because it's less steep but downhill. Okay, so that's what we mean when we talk about gradients. What is the gradient of this line? So as we said before, you want to pick like whole number points that go through these intersections if you can find them. Sometimes you just can't find them. Here I think I can find one. I think that is going right through an intersection there. And I think I can find another one where that one seems to go. That doesn't quite, but that one does seem to go through there. Okay, so then I ask myself, to get from this point to this point, how much do I have to go up? Well, I'm going from this point down to here. So I'm going down to there. So that's from 16 down to, well, that'll be -20. So that's going to be -36. And then how much do I have to go across? And that's going to be from 2 to 18, so that's going to be 16. So the gradient of this line is -36 over 16. And we can cancel that down. 4 goes into that 4 times, and 4 goes into that 9 times. So -9 over 4 is the gradient. Or if you want to decimal it, -2.25 is the gradient of that line. So that's how we find a gradient of the line. We want to pick 2 points, ideally quite far apart. And ideally, if you can find good points fall on the crosshairs where these grid lines meet. So if you can find one of those, but you can't always. Find the gradient of this curve. Okay, so we can't really find a gradient of a curve. A line has the same gradient all along, but a curve, well, it's called a curve because its steepness is all the time changing. Its gradient is always changing. So it's not right to ask that question. You'd be much better off asking the question, find the gradient of this curve at a particular point. So let's choose the point here at x is 4. Let's find the gradient at x is 4. So what I want to do is I want to draw a tangent to the curve. Now a tangent is going to be a line, and we'll draw it in a nice say purple color and not too thick. So it's going to be a line. Now that line isn't a tangent because it cuts the curve in, well, you can see it cuts it in two places. It might cut it in a third place over there as well. So that would be called a chord. Well, this bit of it would be called a chord, right? Now this wouldn't be called a tangent. What I need to do is I need to find a tangent. Tangent will only touch the curve in one place. So that's sort of touching it in just one place, but I think it's touching it here, slightly off of where I want. So why don't I make my line a little bit steeper? A little bit steeper. And what I'm really trying to do is match the steepness of the curve. So I'm just trying to match the steepness of the curve. And I think that's about it. And I want to make that line as long as possible. So I'm going to make it as long as I possibly can. And then to work out the gradient of that line, I'm going to pick those 2 points on it. Now I can't see that that line goes, well, it sort of does. I think that's sort of a whole number point, and that's sort of a whole number. It's not quite there. Maybe I won't choose that because I can see it does miss by quite a bit. Okay, so I can't really find any whole number. I'm also not quite 100% happy with that line. I still want it to be a little bit steeper like that. Okay. So, you know what? I'm just going to choose the end points of the line. I'm just going to choose this point here and this point here. And I'm going to have to sort of guess those y values. So that's 4 and that's 6. So that would be 5. I'm going to guess that that's 5.5. That's a y value of 5.5. And then this y value down here, I'm going to guess that that is, well, that will be -1. So I'm going to say that's -1.25, -1.25. Okay. So the gradient is up. So from here to here, how much do we have to go up? To there. How much do we have to go? Well, we know that's -1.25, and we know that that's 5.5. So that's going to give me 6.75. 6.75. And how much do we have to go across? Well, that's just 10. 10. So the gradient is 6.75 over 10, which is 0.675 is my gradient. So there's my attempt at finding the gradient of that curve. I didn't get it going through any whole numbers. I mean, this looks pretty good, but none of the others look very good. That one there didn't look that great. So I ended up just trying to, as best as I could, calculate. Of course, if you had a grid with minor grid lines as well, so maybe 10 markings between the 0 and the 2, then you could read it off a lot more accurately. So when I give you the questions in the homework, you will have that. You'll have that grid. So although this is your first question that you've got to do, and although you need to find the gradient of this curve here at x is 2, so you need to add the tangent to the curve, and then you need to find the gradient of that tangent, and then you've got to do the same at x equals 4. You've got to find the gradient. So there's 2 gradients you've got to find to that curve, and the one that you'll print off, which will be linked below the video, that one will have a minor grid lines as well, so you'll be able to read it a lot more accurately. Okay, so that's your first question. Areas. Find the area of this curve between x is 1 and x is 5. So what they're asking us for is this area here. This area here. The area underneath the curve. All of this yellow area. And what I'm going to do is I'm going to divide that up into 2 bits. I'm just going to cut it here. So I'm going to use just a dotted line just to show I'm cutting it there. And the reason is that each side is now a trapezium. So this is a trapezium here. And so is the other side a trapezium. And we know how to work out the area of a trapezium. Whoops, that's not a good idea. And we know how to work out the area of a trapezium. It's a half HA plus B. So the area of this would be a half. H is the gap between the parallel sides. So that's going to be 3. A is one of the parallel sides. So that's going to be 4. And B is the other parallel side. And I can read from my y-axis that's going to be 10. And so that's going to give me a half times 3 times 14, which is 7 times 3, which is 21. So this is 21 units squared. And let's do this one now. We're going to do exactly the same thing. A half, H is going to be the gap between the two parallel sides. So that's going to be 3 again. A is going to be one of the parallel sides. So that's going to be 10 again. And B is going to be the other parallel side. And I'm reckoning that's 7. So 7. So that's going to give me a half times 3 times 17, which is 51 over 2. 51 over 2 units squared. So this one here is 51 over 2 units squared, which is 25.5. Add it on to the 21, and that gives me 46.5 is my total area. So the total area is 46.5 units squared. Okay, so there's my area under that. I just used the area of a trapezium. Nothing more complicated than that. Find the area under this curve between x is 1 and x is 4. So this time it's this area that they're after. Between x is 1 and 4, underneath the curve, is this area here. So that's the area that they're after. And this is a little bit more tricky because it's a curve. The other one was straight lines. So I can't work this out. Not at GCSE level I can't work this out. So what I'm going to do is approximate it instead. And the way I'm going to approximate it is I'm going to break it up into 4 separate trapezia. So let's do the first one. And I'll do that in green. So I'm going to do a line like that, a line like that, a line like that, and then a line just connecting those 2 points straight across. Now that green trapezia, its area is not going to be the same as the blue area. So I'm going to be underestimating it at the moment. It looks like I'm going to be underestimating, but it's the best I can do. So I'm going to carry on and just see what I get. Okay, so this area is going to be a half. H is the gap between the two parallel sides, which is 1. A is this length here, which looks like, well, that's 2, that's 3, that looks like 3.5. 3.5 plus B is, well, that's bang on 5. So 5. So that gives me 8.5 divided by 2, which is going to give me 4.25. 4.25 is that area there. Okay. Now I'm going to move on and do the next one. And I'll do that in blue. So the next shape I'm going to draw is this trapezium here. This one's actually a lot more accurate. This one's actually it's still an underestimate, but it's a lot more accurate. And I'm going to work this out. It's going to be a half times the gap between the two parallel sides is 1. The first parallel side is 5. And the second parallel side is, well, that looks like 3.5 again. And so that's going to give me 4.25 all over again. So those two trapezia are identical, really. They're just, one is flipped in the vertical. Okay, we've got one more shape to do. So we'll do this one here, and we'll do this in, say, purple. So that's going to be our shape of our trapezium. Okay, and this time it's the trapezium that I've drawn is slightly bigger. It's going to slightly overestimate. So the first two were underestimates. The last one is going to be a slight overestimate. When you're doing a lot of these, those overestimates and underestimates sometimes just cancel out each other out. So you end up with a good approximation at the end of it. Okay, so the last one is a half. H is the gap between the two parallel sides, which is 1. A is that, which is 3.5, plus B is 2. And so that gives me 5.5 divided by 2, which is 2.75. Okay, and then I'm just going to add all of these three up together. And so that's going to give me 8.5 plus my 2.75 is going to give me 11.25 units squared. Now I reckon the real answer is slightly more, because I underestimated by this amount, but then I overestimated by this amount. They look as though they're going to cancel each other out, the underestimate and the overestimate. But then also I underestimated by this amount, which looks quite big. So I reckon the real area is probably more like 11.3 or 11.4. I think I'm going to be a little bit out on that one. But that's how we would approximate an area if we've got something curvy that we need to find the area of. Okay, kinematics. Kinematics is the study of motion, and we'll be largely doing that using displacement time graphs and velocity time graphs. And we're going to use T to stand for time, X is going to stand for displacement, V is going to stand for velocity, and A is going to stand for acceleration. Okay, so what is displacement? Well, it's distance, but it's not exactly the same as distance. So displacement is how far you are from where you started. So if I go for a walk to the top of my road, then that might be like 100 meters. So when I reach the top of my road, you might say your displacement is 100 meters. And I'll say to you, yes, my displacement is 100 meters. And then you might also say the distance you've traveled is 100 meters. And I'd say, yes, the distance I've traveled is 100 meters. But then when I start walking backwards and go back into my house, now, well, the displacement is how far I am from where I started. I started at my house, I walked to the top of my road, but I walked back. So now my displacement is 0. I've not actually traveled anywhere. I mean, I have, but I'm not any further from my house than I started off. Whereas my distance travel will be 200 meters. So if you were doing that, if you were like a robot doing that, there'd be no point in it. There'd be no, why'd you walk up the top of the road and down? If you're a human doing it, there might be a point in it. Maybe you say I was getting some exercise or I was getting some fresh air. But you couldn't use that argument if you're a robot. Okay, so it's not quite the same as distance, but it's kind of the same thing as distance. Velocity is kind of the same thing as speed. When I was walking up to the top of the road, my speed that I was walking might have been 3 meters per second. When I was walking back, my speed was also 3 meters per second, but my velocity would have been -3 because it's in the opposite direction. And velocity is like speed, but it can be negative, whereas speed wouldn't necessarily be negative. It would just always be positive. But also, later on, velocity can be a vector, whereas speed can't be a vector. But anyway, that's much later on. Okay, so now we're going to look at some displacement time graphs, and we're going to investigate. So we'll do that using GeoGebra. What I've got is, well, I've got a nun on a scooter, and it says here run the nun. I've placed some points here to set it up first of all. So run the nun. So let's click on run the nun. Okay, so what you saw was she ran for about, well, she scooted for about 6 meters, and then she stopped, and then she turned and went back again. So let's try her again. Okay, she's running, she's stopping, and now it's slower. When she's coming back, it's slower. Okay. Let's try it once more. Okay, so that's on the way there, 6 meters, done in very quick time, and then a lot slower. So what we see, this is my displacement graph for her motion, and on the graph she's only moving, all she's doing is moving along the road. She's just moving 6 meters along the road and then back again. So So she's not moving in 2 dimensions, she's just moving in 1 dimension. But what you see on my graph is you see that she starts off and her displacement is 0 and time is 0. And then for the first 3 seconds, she's moving. And so we see that as the time goes on, her displacement increases. And by the 3rd second, she's now 6 meters from where she started. And then for the next 3 seconds, from t is 3 until t is 6, she's just stationary. So here she's just turning her scooter around. She's not going anywhere. And then now, over the next 6 seconds, she goes back more slowly. She goes back more slowly because it only took her 3 seconds to get there, the 6 meters back. And what you see is her displacement is going down. Her distance travelled is going up because from here to here she moved 6 meters and then she moved another 6 meters back. She's done 12 meters worth of scootering, yeah, which is good. But her displacement by the time she gets back is 0. So what you see is the displacement is going back down. So this line going downwards shows her going in the opposite direction. So on a displacement time graph, if the line has a downhill gradient, it means that the direction is the opposite from the normal direction, from whatever direction you define as positive. Okay, if we find the gradient of this line, that will tell us how fast she was going. And we know that gradient is up over across. So I'm going to choose this point and this point. I'm going to say I'm going to go 6 up and then 3 across. So 6 over 3 would be 2. So she was skateboarding or scootering at 2 meters per second here. And then on the way back, I'm going to work out the gradient from here to here. And so I'm going to say, how much does she have to go up? Well, she doesn't go up, she goes down 6. And how much does she go across? She goes across 6. So from here to here is 6. So the gradient for this bit will be minus 1, down 6 will be minus 6, minus 6 over 6, which is minus 1. So the gradient for that second bit of her motion would be minus 1. So what we see on this displacement time graph is, yes, you can read how far she is at any particular time. So if you want to know where she is at t is 2, she's 4 meters. If you want to know where she is at t is 4.5, at t is 4.5, she's 6 meters from the convent. If you want to know where she is at t is 8, at t is 8, she's 4 meters from the convent again. But also, by reading the gradients of these lines, that will tell us the velocity, that will tell us the speed, but actually, because gradients are positive and negative, that will tell us the velocity more specifically. Okay. So, on a displacement time graph, time is on the x-axis, displacement is on the y-axis, and velocity is the gradient at any point. So if you find the gradient, that will give you the velocity. Okay, so what have we got here? We've got a little spider, and there's a thread here, so he can climb up and down his thread. And we've got a displacement time graph, and let's animate it and see what happens. Okay, so he's moving up, he's going quicker, he's going quicker. Oh, he's slowing down now, he's slowing down. Okay, now he's stopped, he's not moving. And now he's going back down, and he's going faster, and then now he's going slower and slower and slower. Okay, let's click on show velocity calculation, and then let's animate it again. And this time it's showing us the gradient. You can see it's working out the gradient at each point. And you can see that here the gradient is minus, you can read the gradient off of it. It's doing 2 points and it's working out the gradient. So I'll just try and just do that again. So you can see the gradient's going up and up and up and up. Now it's staying at 2, now it's staying at 2, now it's going down, now it's going down. Now the gradient is dropping to 0 and it's just going to stay at 0 all this way here. Now it's gone negative and it's increasing, gone down, oh, and -2, and then it's gone back up to 0. Okay, so we can plot that velocity time graph. So we can show the velocity time graph as well. So I'm just plotting these values. I'm plotting those values. Okay, so let's go back over that. On the displacement time graph here, remember the gradient gives us the velocity. So here the gradient is 0, but the steepness is constantly increasing here. So during this pink bit here, the steepness is increasing, which means the gradient is increasing, which means the velocity is increasing. So what you see is the velocity is increasing here. So the velocity starts off at 0. Let's just get rid of that. The velocity starts off at 0, and then it goes up and up and up. And by 2 seconds, by here, he's got a velocity of 2 meters per second. Now here we have a straight line, and so that means the steepness is not changing, which means the velocity is not changing. So between here and here, we get a velocity of 2. So on a velocity graph, this horizontal bit just means you're going at the same speed. It doesn't mean you've stopped. Here on the displacement time graph, that bit means you've stopped. But on the velocity time graph, that just means you're going at the constant speed. You're not speeding up, you're not slowing down. Okay, so from here to here, what you see is the gradient is getting less and less and less and less. And so you see his velocity is getting less. And by here, the gradient is 0. So you can see the velocity is decreasing and decreasing. And by 6 seconds, the velocity has dropped to 0. Now this bit here on our displacement time graph, that means that he's not moving. He's stationary. And on a velocity time graph, stationary is when your velocity is 0. So you have to be on the x-axis to be stationary. And so now what we see is he's now heading in the opposite direction. Remember, with a displacement time graph, if the graph starts going back down towards the x-axis again, then that means he's moving in the opposite direction. And so he's moving in the opposite direction, and the gradient is increasing in a negative way. That's a negative number, but it's increasing. And so what you see is this negative number is getting bigger and bigger and bigger here, and gets to -2. So that's here has got a velocity, the spider's got a velocity of -2 meters per second. Then it's, for that period, it's just staying at a velocity of -2 meters per second. And then here, the gradient is, going back to 0. It's -2, then it's going to be -1, then it's going to be 0. Okay, and so what you see is the gradient goes back up to 0, and then the spider has stopped there. So this you can tell on the displacement time graph that the spider didn't get back to where it started. You can tell it didn't get back to where it started because it starts here. It'd have to end on the x-axis somewhere to get back to where it started. So it doesn't get back to where it started. You can't tell that on the velocity time graph. You can't tell it by looking at the velocity time graph that the spider didn't get back to where it went. What you can tell from the velocity time graph is it started off moving in one direction, speeding up, then going steady speed, then slowing down. And then after a little way, it moved in the opposite direction. The bit below the x-axis shows you're moving in the opposite direction. So on a velocity time graph, below the x-axis means you're moving in the opposite direction. Now, on the velocity time graph, we can do another thing as well. We can work out what the displacement was. So if I want to work out the displacement here up until t is 6 seconds, I know from the displacement time graph that it's 7. The displacement is a displacement time graph. If I look up 6, it tells me the displacement is 7. Where is that on this diagram? Well, where you'd work that out in this diagram is you'd find the area underneath this shape here. Okay, so you can chop it up like we did before to a triangle, a rectangle, and a triangle, or you can notice that this is a trapezium. For ease, I'm just going to say this is a triangle, and its area is half base times perpendicular height. So that's going to be half of 2 times 2. So that area is going to be 2. And then this area is a rectangle. So this area is just going to be the width times the height. So that's also going to be 2. So that's got an area of 2. That's got an area of 2. This is again a triangle. So it's going to be a half base times height. And that's going to be 3. So we've got 2 plus 2 plus 3 gives us a total of 7 meters. So the area underneath here is 7. And that tells us he's 7 meters away from where he started. Okay, so that's what's going on a velocity time graph. Yeah, a little bit more complicated than a displacement time graph, but you can find displacement on the velocity time graph. You can also find one more thing. Remember earlier on we were finding the gradient on the displacement time graph and saying that that gives us the velocity. On the velocity time graph, if you find the gradient, so if I find the gradient from here to here, the gradient's 2 up, 2 across. So this gradient is 1. So that tells me during this bit here, he's accelerating with an acceleration of 1 meters per second squared to reach a speed of 2 meters per second. And then he carries on going at 2 meters per second for a second. And then he starts slowing down, still going upwards, but it's not, his speed is reducing. And he slows down, and at 6 seconds, he stopped. He reaches a speed of 0, a velocity of 0. And then for the next 2 seconds, he just sits there for 2 seconds, doesn't do anything. And now he's speeding up, but in the opposite direction. So his velocity is negative, and it's an acceleration of -1, because it's a gradient of -2 up, 2 across. So the acceleration is -1 meters per second squared. So there's an acceleration of -1 meters per second squared until he reaches a speed of -2 meters per second. Then it's steady speed of -2 meters per second for a second, and then slows down to a stop. And this area is going to be, well, that area is 7. This area is going to be 5. And because this area isn't as big as this area, that's how we can work out he didn't get back to where he started. So that's a velocity time. Actually, mathematicians much prefer velocity time graphs because you can find everything on the velocity time graph. You can find the displacement, you can find the velocity, you can find the time, you can find the acceleration. From here, you can of course find the displacement and the time. Finding the velocity becomes a little bit more tricky on here. And the reason finding the velocity becomes a little more tricky is you've got to do that thing where you do the gradient. So you've got to find the gradient of that line to find the velocity. And you know, how good is your line going to be? How accurate is your tangent going to be? So, you know, you can find it on there, and you can't find acceleration on here at all. Whereas on this one, you can find everything. You can find velocity, you can find acceleration, you can find displacement, and you can find time. So it's all going to work out really nicely. Okay, we'll put that away. Charlie is very forgetful. He left his house, ran to the corner shop 100 meters away, and that took him 25 seconds. He picked up some Oreos and went to the till. He then realized he'd forgotten to bring money, so he put them down and walked away at a slow, dejected 2 meters per second. As he walked through the front door 2 minutes later, after he'd left, he saw his mum standing in the hallway holding out his wallet. Draw a displacement time graph. So I'm just going to abbreviate that question so I've got room for a displacement time graph. So it's the same question. Ran to a shop 100 meters away in 25 seconds. Till he reached till. He realised no money. Then he walked home at a slow 2 meters per second. He was back home 2 minutes after he left. And it asked us to draw a displacement time graph. So y is actually going to be displacement. So I'm just going to change that. Actually, I'll get rid of it by making it white. And I'll change that to displacement in meters. And I'll make this into time in seconds. Okay, so I know that he started off at home. So at t is 0, he's at home, and I'm saying at home is 0. But in 25 seconds, he'd got 100 meters away. So he was there. So that was him moving away at over 25 seconds, he'd moved 100 meters away. And then he stayed here for a certain amount of time, but I don't know how long he stayed here for because they don't really tell me that. So I don't really know how long he stayed there for. Just going to guess. And then he walked home at a slow 2 meters per second. Okay, so I know that the final bit of the line, I'm just going to draw it in red, the final bit of the line. And I know that this final bit of the line has got to have a gradient of 2. So I don't know what a gradient of 2 would look like on this diagram. So I'm just going to put it like that. And I'm going to say, look, its gradient has to be 2. So the gradient has to be -2 because it's backwards in the opposite direction. The speed is 2 meters per second. The velocity is -2 meters per second because it's in the opposite direction. And so the gradient gives you the velocity is -2. And I know that gradient is up over across. That's how we work it out. Gradient is up over across. So I know from here to here, well, I know, of course, he's got to go back 100 meters. So up is -100. over across. I don't actually know what across is. Remember, I just guessed this, so I don't know what across is. So I'm going to leave across as question mark. So that's going to be minus 100 over, and across is just going to stay as question mark, or I'll call it t as the unknown time. And so that gives me an equation, minus 2 equals minus 100 over t. And so that gives me t equals minus 100 divided by minus 2, so that's going to give me 50. So t is 50. So I know it took him 50 seconds to get home. And I know he was back home 2 minutes after he'd left. So if I just move that to 120 seconds, 120 seconds is 2 minutes. And I know that this has got to be 70 seconds. I know this end of it has got to be at 70 seconds because that will be 50 seconds back from 120. So that's got to be like that, which means that's got to be like that. And that's got to all move like that. Okay, so that's made it correct. That's now minus 100. That's now 50. Minus 100 over 50 will give me minus 2. Okay, so I figured it all out. What did it say? It said just to draw the velocity time graph. So I've drawn my, the displacement time graph. I've drawn my displacement time graph. That's all they wanted me to do. It's a little bit more fiddly here because they gave us a bit of the information about how long he'd been stationary for. They didn't tell us. Okay, velocity time graph. So we're moving on to look at velocity time graphs. So I've pulled up another GeoGebra screen for a velocity time graph, and I've got a velocity time graph. I've moved the points to where I want them, and so this is my velocity time graph. So what I know with my velocity time graph is that I can convert it into this displacement time graph. So this and this represent the same journey. So from here to here, what you see is on the velocity time graph, the velocity increases from 1 to 4. Where is that on here? Where is that? It's this bit here. And what's happening is the gradient here is increasing from 1 to 4. And I'm going to show you that because I'm going to show you the tangent here. I'm going to move the tangent here to 0. Okay. And, let's just move it a little bit. It won't draw a tangent if I'm at 0. So I'll just move it a little bit away from 0. So I've gone a little bit away. I'm going to pick 2 points on the tangent. So I'll pick nice far apart points. I'll pick this point and this point. Oh, that goes so nice. And I'll ask it to work out the gradient. And it says the gradient there is 1.2. And remember, the gradient there was 1. Okay. So if I move this to t as 1, what you should find is the gradient increases. And at t is 1, we know that the speed should be 2.5 and the steepness of that is 2.5. So the gradient of this displacement time graph is just telling you the velocity on that original graph. By the time we get to b, we're at a gradient of 4, and we know that by the time of b, the speed is 4. Okay. All right. Let's look at the next bit of the graph. So here, from here to here, you've got steady speed, and steady speed on a velocity time graph is just horizontal. But on a displacement time graph, that will be a straight line, but it wouldn't be horizontal. Horizontal would mean you're stopped on a displacement time graph. So that bit here is its gradient is going to be 4. Because that's the speed, and the gradient of the displacement graph gives me a fig. So again, I'm going to do the same thing. I'm going to say, let's have a look at the gradient here. So the gradient here, you can see wherever I choose on here, the gradient is 4. I'm going to pick some points that say I'm about here on my line. And I'm going to pick, say, this point here, and I'll move, I've lost the other point, haven't I? My tangents, there it is, just went a bit further away. Okay, so say I'm here and I'm going to choose that and I'm going to make that my second point, and you can say that I'm going up 20 and across 5, so gradient is 20 over 5, which is 4. And so you want to pick 2 nice far apart points and then work out what the gradient is. So this is my displacement time graph. As I carry on up this displacement time graph, you can see here that the speed is getting less. So if I get to, say, here, that point there, I can see from my velocity time graph that the speed should be 3, and I can see that the gradient of the curve here is 3. And again, you can move the points P and Q. You can move them a little bit further apart so you get a nicer calculation. Sort of jumping across for me, so it's not working out too brilliantly. Okay. And then what you see is as you carry on going here, the gradient gets less and less and less and less and less and less. And by the time you get to here, the gradient will have dropped to 1, which is what it started off at. And then I could change my graph. I could say, look, let's make this, let's make this, let's move these off. I could move this point. I could make that a little bit steeper acceleration. And I could move this point here. So it moves to, that's a steeper deceleration. And what you see now is you see that the acceleration phase here, you're going to go from a gradient of 1 to a gradient of 14. So that's gone all the way up to a gradient of 14. I know it says 15, but it's actually 14. And then here we've got that gradient is gone, and then it very quickly decreases in gradient. Okay, so that's what's going on there. Okay, so on our velocity time graph, time is on the x-axis, velocity is on the y-axis, acceleration is the gradient at any point, and as we talked about before, displacement is the area underneath the curve. So if we want to find out what the distance travel is, we'll work out what the area underneath the curve is. So at t equals 0, the traffic camera on the A41 sees a car accelerate uniformly when the lights went green. So he was stationary, then the lights went green, he accelerated. At t is 10 seconds, he's reached his maximum speed of 30 meters per second. He keeps this speed for 20 seconds, at which point he brakes because there's a roundabout ahead and decelerates at 6 meters per second squared. 4 seconds after he started braking, he enters the roundabout. So he won't have stopped, because you can enter a roundabout, you don't have to have stopped to go into a roundabout unless there's cars already coming across you. How long is this section of the A41? Okay, so again, I've abbreviated the question up here so that I've got space for a grid. Okay, so I'm drawing a velocity time graph this time, not a displacement time graph. So I know that he started from rest, and I know that by 10 seconds, he'd reached a speed of 30 meters per second. So by 10 seconds, he'd reached a speed of 30. So I think that's 10 and that's 30. Okay. Maintains this speed for 20 seconds. So keeps this speed for 20 seconds. So that's until t is 30. So that's until... Maintains this speed for 20 seconds, so that's until t is 30. I haven't left enough room on my grid. Until t is 30. Okay. And then he brakes for 4 seconds, decelerating at 6 meters per second squared. Okay, so we know that the gradient for the next bit is going to be -6, because that's going to be a deceleration. So we know that the gradient of this bit, the gradient is going to be -6. And remember, we said that gradient is up, over, across. And we know that it's across for 4 seconds. So we know this is 4 seconds. 4 seconds. So -6 equals up over 4. And so up equals -24. So we know that this is -24 up. In other words, down 24. So he's at 30 meters per second, and he's gone down by 24. He's dropped 24 from there, so he ends up at 6 meters per second. So this should end up at 6 meters per second. Okay, it's kind of gone off the grid, but that's all right. We can still work with it. Okay, so I'm just going to put some extra numbers on here because it's gone off the grid. I'm just going to put some, just gently put some numbers on there. So I know that that is, so this was at 10 seconds. So this was at 10 seconds. Then he was going at steady speed for 20 seconds. So this is 30 here. And then this point here is at 34 and that y value is 6. Y value is 6. Okay, and so there's that motion. So the motion looks like this. He's uniform acceleration, steady speed for 20 seconds, and then braking, but not to 0, just to 6. Okay, and then he enters the roundabout. And we need to know what the distance travelled is. And we said that on our velocity time graph, the area will give us the distance travelled, or the displacement. So I'm going to break that area up into 3 separate bits. I'm going to work out this bit, and then this bit, and then I'll work out the last bit. So the first bit is a yellow triangle, the second bit is a green rectangle, and the last bit is a blue trapezium. Okay, so let's work out those areas. So do the first one, I think we'll do that in red. So that's a triangle, so it's a half times the base, which is 10, times the height, which is 30. So that's 300 divided by 2, so that's 150. So this is 150 meters, this bit here. Okay. Next one is just a rectangle, and a rectangle is just length times width. So that's 20, and that is 30. 20 times 30, so that's going to be 600. Is that bit there. And then the last bit is a trapezium, which is a half h. H is the gap between the parallel sides. These are the parallel sides, and that's the gap between the parallel sides, so that's 4. And then one of the parallel sides, which is 30, plus the other parallel side, which we know is 6. So that's going to give us 36 times 2, which is 72. So that's going to give us 72 meters. Okay. And so we know that the distance travelled until he reached the roundabout was 600 plus 150, so 750, plus 72. So that's 822. So that's 822 meters. So we know that it was 822 meters from the traffic lights, to the roundabout. We also know that he hit the roundabout going at 6 meters per second already. Just to give you a little bit of an idea, because I'm using meters per second, and in maths and physics we use meters per second. But of course, when you're driving a car, well, here we use miles per hour. The rest of the world uses kilometers per hour, but here we use miles per hour. And so just to give you a quick heads up, if you want to change from meters per second to kilometers per hour, you just multiply by 3.6. So over here, we know he's going at 30 meters per second. So 30 meters per second, 30 meters per second. Well, if we times that by 3.6, that's going to give us 90 and 18, 108 kilometers per hour. Now remember, to change from kilometers per hour to miles per hour, you already know that that's times 5/8. Times 5/8. So times 5/8. So 62% of that, or something like that. That's going to be about 65, 67 miles per hour, something like that. Okay, just approximately. That's not an accurate conversion. It's approximate. This is an accurate conversion. This is equal. Okay. So 30 meters per second equates to 67 miles per hour. So that's a pretty high speed. That's sort of motorway speeds. Okay. I'm a lethal soldier. So this is your question 2 and question 3. At Tiers Nord, I see in my scope a military drone. It's 1,000 meters away from me, moving at 30 meters per second towards me, and still accelerating. And its acceleration is 4 meters per second squared. These drones have a top speed of 50 meters per second, but they're noisy at 50 meters per second, so easy to see and shoot down. After 2 seconds at top speed, my commander shoots it and hits. It continues to glide towards me, but it's now decelerating at 2.5 meters per second. I guess that it's still moving towards me, but when you're moving that fast, there's a lot of wind resistance, and its motors are no longer propelling it to keep going at 50 meters per second, so it's going to slow down. Kind of in the same way as if you disengage the engine and you're going at 50 meters per second, your car won't stop, it will just slow down. It will just naturally slow down if you disengage the engine. So it's slowing down, it's decelerating at 2.5 meters per second. And this is the horizontal, all these are horizontal speeds and acceleration, but now they tell us it's also falling. 8 seconds after it shot, it hit the muddy ground, but I can't see it now because it's in the mud. I can't see it. Draw the velocity time graph of the motion. I want to retrieve it. Tell me how far from me it is. So how far is it from me? So you're going to say, look, when you started looking at it, it was already going at 30 meters per second. So you're already going to start at 30 meters per second. And then it's accelerating at 4 meters per second squared. So the gradient of this line is going to be 4. So the gradient is going to be 4. And you know that gradient is up over across. And you know that it's got to go up by 20 because it's got to reach a speed of 50. So up is going to be 20, which means you can figure out what across is going to be. You can work it out. And then you can draw the line in properly. And once you've drawn that line in properly, then you can draw it going at steady speed for 2 seconds, however long 2 seconds is. And then after that, you can draw it decelerating for 8 seconds. So it's 8 seconds and it's decelerating. And you know that the gradient of this bit here is minus 2.5. So gradient is minus 2.5. So you want to know what up is. Well, it'll be negative up. So minus 2.5 gradient equals up over across is 8, and then you can work out what up is. It'll be a negative number, and then you can work out what that final speed was when it reached the end. My diagram's rubbish. I'm just giving you some guidelines for how to do it. You've got to draw your velocity time graph properly, and then I want to retrieve it. Find out tell me how far it is from me. Well, you can work out the distance it's traveled, but that might not be the same as the answer. You can split it into 3 areas and work out the distance traveled, but that might not be the final answer. There might be one other thing to do. So this is our classroom practice. We've got some displacement time graphs here, 3 of them, with lots of information on them, and we want to convert them into velocity time graphs. And then we've got these 2 velocity time graphs, and we want to convert them into displacement time graphs. And in each case, I'm also going to ask you, give me an example of that situation. What could that be? What situation could that be? So I'm just going to ask you, what might that situation be? What might this situation be? And then we've got an actual question at the end. A tile falls off a spacecraft which is moving at 400 meters per second. Oh, that's fast. So it's going at 400 meters per second and the tile just drifts off of it. The spacecraft doesn't even notice and he fires his rockets, accelerating at 50 meters per second squared for 12 seconds. How far apart are they at the end of the 12 seconds? Okay, so that's your final question. Don't forget to hand in your corrections to the previous homework and make sure you prepare for the test. I will see you in the next lesson primer. Mena will see you at the weekend. Bye.